Let's look at some examples in Proton NMR. So there I've drawn the structure of ethyl ethanoate, and hopefully we can see that there are three different proton environments, and we can see in the spectrum above that we've got three peaks. Perhaps the easiest ones to identify then from the spectrum, the ones where the integration value is 2, so that's been caused by the two protons, so that is the green ones, and their chemical shift. So if we have a look at the table on the right hand side there, we can see that here we've got protons on a carbon next to an oxygen in an ester will be appearing around about 3.7 to 4.1, which is roughly where they're coming in. So now for the other ones, if we look at our yellow protons, so they're on a carbon next to a carbonyl group, so we'd expect to be seeing them from 2.1 to 2.6, and also in terms of the splitting, so there are no hydrogens on the adjacent carbon to the yellow hydrogens, so there's no neighbours, which means that would appear as a single peak, a singlet, which is that one. And then finally, just to confirm, the blue protons, so not in a particularly interesting environment, so just next door to a CH2, so we'd expect them to be down the right hand side, and they have two adjacent hydrogens, so 2 plus 1 is 3, so they would be split in 3 as a triplet, and that's what we can see there. Let's take a look at this final example. So looks like quite a large molecule. We're told that it has a ketone as well as an ester functional group, so that would account for those 3 oxygen atoms in its formula. First thing that we can note from the spectrum is that there are 5 peaks, which means there are 5 different proton environments. Now the ratio has been given as 0.8 to 0.8 to 0.8 to 1.2 to 1.2, so they've not given us the numbers straight away there. If you imagine that was an 8 to 8 to 8 to 12 to 12, and if we simplified that down, then we would get 2 to 2 to 2 to 3 to 3. And if we add those up, we get to 12, so 12 hydrogens in our compound. The next part of the question is asking for the part of the structure which can be deduced from the peak at 2.2. So here we are, the peak at 2.2, and we know its integration is 3, so that's been caused by 3 equivalent protons. And if we look at its chemical shift, then we would probably suggest that these are protons next door to a carbonyl group, and also the fact that we've got a single peak there, a singlet, means that we're expecting to have no neighbouring hydrogens. Next we're looking at the peaks at 4.13 and 1.26, and that we're told that they're arise from the presence of an alkyl group. So for this fragment, from the red peak there, the triplet, we can see that we've got 3 equivalent hydrogens, and the shape of the peak being a triplet means that they're living next door to 2 others, and this goes hand in hand with the green peak, so that we can see we've got 2 equivalent hydrogens, and since that's a quartet, they must be living next door to 3 others, which gives us an ethyl group. And finally on this, just from the chemical shifts, so the red peak at 1.26, so we're looking at just some standard hydrogens there, but for the peak down at 4, then that's looking like we've got some hydrogens next to an oxygen. So we might suggest that the next thing on there is an oxygen. We're now looking at the peaks at 2.76 and 2.57. I'm looking at another fragment of the molecule. So we can see that we've got 2 CH2s, so the integration value is 2, and we also have 2 triplets, which suggests that we've got 2 hydrogens on the adjacent carbon, which would work for a CH2-CH2. For the chemical shift for these protons, it would appear that they're both just around about 2.5, just above, so they both may well be protons next door to carbonyl groups. So we know that we've got both an ester and a ketone in this compound, so that might be a good suggestion. So finally, trying to deduce the structure of the compound, these are the 3 fragments that we're suggesting, and a little bit like a puzzle, if we move them around, try and work out where they all go, then that would make the ester group there, and then the left hand side we can probably see that that will overlap there, which leaves us with that as compound X. And one final example, so we've got C5H10O2 and we're told it has 4 peaks, so let's look at the peaks individually. The first one at 2.18, so this has an integration value of 3, so that's suggesting we've got a CH3, and since it's a singlet, so there are no hydrogens on the adjacent carbon, and the chemical shift of 2.18 leads us in the direction of a carbonyl next door. Next, we're looking at the peak at 3.33. Again, it's a singlet. Again, it's a CH3. But the chemical shift this time, suggesting that next door to the carbon, again, it's a singlet, so those hydrogens have no neighbours. Looks like we've got an oxygen. Finally, we've got the 2 triplet peaks. and these are both for CH2s. So we've got 2 hydrogens next to 2 others and 2 hydrogens next to 2 others. So that's the 2 triplets that we see. They've got slightly differing chemical shift, so one of them's coming in around 3.5. So this would suggest that we've got the hydrogens next door to an oxygen, whereas at 2.59 then we've probably got the hydrogens next door to a carbonyl group. So that would complete that fragment. Let's put the structure together then. So let's move our pieces round to try and solve the puzzle. So that oxygen is going to be that oxygen there, and that carbonyl group will be the same as